Physics part 136. Conservation of energy, Kirchhoff's second law. Charge flowing around the circuit gains electrical energy on passing through the battery and loses electrical energy on passing through the rest of the circuit. From the law of conservation of energy, we know that the total energy must remain the same. The consequences of this conservation of energy is known as Kirchhoff's second law. The law may be stated as the sum of electromotive forces in a closed circuit is equal to the sum of the potential differences. The figure shows the circuit containing a battery, lamp, and a resistor in series. Applying the Kirchhoff's second law, the electromotive force in the curved circuit is the EMF E of the battery. The sum of the potential differences, the PD V1 across the lamp plus the PD V2 across the resistor. Thus E is equal to V1 plus V2 if the current in the circuit is I and the resistance of the lamp of the resistor are R1 and R2 respectively. The PDS can be written as V1 is equal to IR1 and V2 is equal to IR2. So E is equal to IR1 plus IR2. It should be remembered that both electromotive force and potential differences have directions. This must be considered when working out the equation for Kirchhoff's second law. First example, in the circuit of the figure, two cells have been connected in opposition. Here the two electromotive force in the circuit is E1 minus E2, and by the Kirchhoff's second law of E1 minus E2 is equal to V1 plus V2, which is equal to IR1 plus IR2. Internal resistance. When a car engine is started while the headlights are switched on, the headlights sometimes dim. This is because the car battery has resistance. All power supplies have some resistance between their terminals called internal resistance. This causes the charge circulating the circuit to dissipate some electrical energy in the power supply itself. The power supply becomes warm when it delivers a current. While the figure shows a power supply which has EMF, E is equal to internal resistance R, it delivers a current of I when connected to an external resistor of the resistance R, called the load. VR is the potential difference across the load, and VR is the potential difference across the internal resistance. By Kirchhoff's second law, E is equal to VR plus V1. The potential difference VR across the load is thus given by VR is equal to E minus V2. VR is called the terminal potential difference. The terminal potential difference is PD between the terminals of the cell when a current is being delivered. The terminal potential difference is always less than the electromotive force when the power supply delivers a current. This is because of the potential difference across the internal resistance. The potential difference across the internal resistance is sometimes called the lost volt. The lost volt is equal to EMF is equal minus EMF. The lost volt is equal to EMF minus terminal PD. In contrast, the electromotive force is the terminal potential difference. When the cell is on open circuit, when it is delivering no current, this EMF may be measured by connecting a very high resistance voltmeter across the terminal of the cell. You can use the circuit in the figure 7.23 to show that the greater the current delivered by the power supply, the lower its terminal potential difference. As more lamps are connected in parallel to the power supply, the current increases and the lost volts given by. Lost volt is equal to current into internal resistance will increase, thus the terminal potential difference decrease.